Hello and welcome everyone. So today we are going to start chapter 11. It is power plant systems. So in this chapter we have two parts. Mainly we will discuss about two parts. So the one is steam turbines and other is steam condenser. So we will first take up the steam condensers because the steam condensers this is structurally very much same as that of shell and tube heat exchangers. So the steam condensers, the main application of the condensers are in power plant systems, steam power plant systems, and along with that, the condensers are widely used in chemical and process industries. So if we see its application in power plant engineering, then we know that it is connected after the turbine in the power plant cycle. So when the steam is exhausted from the turbine, then it goes to the condenser, and where it is condenses into the liquid, saturated liquid, and sometimes it is subcooled liquid. So the condenser takes the steam from the turbine exhaust and then condenses it, and then so after the condenser, that steam goes back to the boiler. So the other side, the cold fluid enters into the condenser, and then it passes through the tubes, and then it goes out of the condenser. So the cold fluid enters, so it's the temperature is less, and then at high temperature it comes out of the condenser. The steam enters the condenser as saturated steam, or sometimes little more sub wet steam, or a little more and a little superheated steam as well. And when it goes out, it is near about saturated liquid. So the steam converted into the saturated liquid, that is why it is called condenser. Whereas when the coolant enters, it takes the heat and its temperature rise takes place. So here you can see the structures of condensers. So it's a giant equipment, and sometimes it is like equal to 2 or 3 classrooms, and and depending upon the capacity. So here you can see the structure of shell and tube type steam condensers. So it has a bundle of tubes inside the shell, and at the top of the shell, as we can see here, this is the inlet for the steam. The steam enters here, and then it passes over the tubes, and while it is passes over the tubes, it condenses, and then it is taken out from this condensate port. As for the coolant liquid is concerned, that the one end, the liquid enters into the cooling tubes, and some if it is one pass, then other end is there is the exit for the coolant liquid, and if it is two pass, then the coolant liquid comes back, and then from the other end it goes out. And then there are different parts, like these are the tubes, and these are the tube plates which supports the tube, and then there are uh, some ports for non-condensable gases out, and there are some safety valves and safety nozzles also. So this is cut section, as you can see here, that the the cold liquid or the coolant enters here, and it goes into the tubes, and then it comes out from here. And as you can see that the steam enters from the top, and then it passes over the tubes, and then it is collected in the bottom of the condenser, and this is we call the hot well. And from the hot well, it is trapped, it is basically tapped outside, and then it is sent to the boiler with the help of a pump. This is a two-pass type of steam condenser, that the coolant liquid, which is most of the cases water, it enters here and then goes in the tube here, and then it comes back through the tubes here and then goes out of from the outlet plenum. So this is we call inlet plenum, and this is we call outlet plenum, and this is the U turn which supports the fluid turning from from lower half to the upper half of the tube. Whereas the steam enters here, this is called the steam exhaust, and passes over the tubes, and it is collected at the bottom of the condenser. We call it hot well. So there are certain advantages associated with the steam condensers. So if we see that it gives us the improved work done and higher efficiency, and it facilitates the operation of the turbine to a low pressure. And when the turbine operates for a larger difference of the pressure, that the inlet and outlet pressures difference is larger, then it produces higher amount of work, and due to that the rate of work done becomes higher and efficiency becomes higher. The another advantage of condenser is the recovery of the condensate. So the working fluid which enters the boiler, and then it is converted into the steam, and then it is passes over the turbine, and after passing through the turbine then it is not basically exhausted into the surrounding, it is recirculated. So recirculated with the help of condenser, because the steam which we are getting from the turbine, it directly cannot be sent to the boiler. So the condenser facilitates the steam get converted into the condensed liquid, and that liquid can be fed through the pump. The pressure is increased by the help of a pump, and then it is sent back to the boiler. So this is how we can save the condensate. So it is reduces the steam consumption because it increases the efficiency. If we consider the same power output, then the steam consumption can be reduced with the help of a proper condenser. Economy of the softening plant, because the water that we use in steam power plants, it is highly filtered and it is desalinated, so we don't want to lose that water. So the condenser basically helps to get that water back, and then we can recirculate in the system. So reduce thermal stresses, with the help of a condenser, what we got the condensate, it's at a high temperature, and then the high temperature condensate is sent to the boiler. So basically the boiler, the work done or the heat supplied by the boiler is reduced, and there is not much temperature difference between the condensate and the steam generated in the boiler. So the temperature difference is reduced as compared, like if you take this boiler supply from outside. So what are the features of good condensing plant? That it should minimize the circulating water, and it should minimize the cooling surface area per kilowatt capacity, and it should minimize the auxiliary power, and it should minimize the condensed steam condensed per meter square of surface area. So these are some features related to the condenser, the advantages and the features. So what are the different elements of condensing plant? As you can see in the schematic, so this is our condenser, and connected to it is the cooling tower. So the condenser takes the liquid with the help of a pump, and from the cooling tower it goes to the condenser, and that it comes out to the cooling tower, and then it is cooled in the cooling tower, and then with the help of a pump it's sent back to the condenser. So in the cooling tower some of the water is vaporized, so we need to make up the water. So we take the water, and with the help of the pump we supplied, and this is equivalent to the makeup water. And this is our steam turbine, and from the steam turbine exhaust it goes to the condenser, and then the steam is condensed, and then it is a condensed liquid, and then it is collected in the hot well, here, and with the help of a pump it is sent to the boiler. Okay, so sometimes due to some impurities involved, the steam contains some non-condensable gases. So when the steam we try to condense in the condenser, and if the non-condensable gases are dissolved in the steam, so those gases doesn't condense. So we need to extract those gases. So there is an extraction pump, we call it air extraction pump, so which extracts the non-condensable gases from the condenser, and it can be thrown out to the surrounding. So if these gases are not extracted, then it is detrimental to the boiler and detrimental to the pump, because these gases will make a kind of a cavitation in the pump. Okay. So there are some common problems associated with the condensers, like the high pressure, the generation of high pressure in the condenser, because the condenser usually we design to work at low pressure, and the corrosion and dissolved gases in the condenser, and the low cleanliness, like if there are impurities involved in the water and the steam, and then that impurity is stuck in the condenser tube surfaces and then create a lot of problems that basically create the scaling and falling over the tube surface, as well as and that results in the low heat transfer coefficient. Sometimes there are dissolved gases, and sometimes because the condenser works below the atmospheric pressure, so the atmospheric airs can leak into the condenser, and that's a problem. So and we don't want that. And there are falling takes place over the tubes, so that is also a problem with the condensers. And the exhaust capacity of the condenser, so the exhaust pump capacity must be maintained to ensure that the proper air removal can happen. So these are some issues that that are very common for the condenser, and we need to take care of them. So here we can see that the impurities or the fallings can take place on the tubes, and here we can see the tube end and how badly it is fall, and impurities and oily films stuck on the surface of the tube. So when we design the surface condensers, so we calculate the heat transfer rate, and we need to determine the tubes and the total surface area required by the condenser. So the knowledge of the so what we need is the knowledge of the total heat load on the condenser, and what is the heat transfer mechanism, and we need to know the heat transfer coefficient and other coefficients of the condenser. So the outside surface of new condensers are usually clean, but quickly they develop oily film over the surfaces, and when the condenser surface is new and polished and finished, then the steam condensation takes place in the dropwise form. And once the condenser is old, and then the oily film the formation of oily film takes place at the surface of the condenser tube, and some impurities also stuck on the condenser tubes. So those things basically doesn't allow the dropwise condensation, and the condensation on the tube surface becomes film wise. So the film-wise condensation usually has less heat transfer coefficient, and the performance of the condenser reduce with that. So we do not want the condenser so that the film-wise condensation happens, but mostly it happens because we cannot avoid the formation of kind of oily films and the impurities stuck at the tube surface. So when the condenser is new, it is film-wise condensation, but very soon it becomes when the condenser is new, it is drop-wise condensation, and very soon it becomes film-wise condensation. The shell side heat transfer coefficient depends upon so there are several factors. So the one of that is the temperature difference between the steam saturation temperature and the tube wall temperature, and then the relative position of the bundle, like how they are placed. the steam velocity and turbulence, and the extent of non-condensable gases and impurities in the steam, and the existence of superheated steam if there is any in the steam. As for the water side, the heat transfer coefficient depends upon the velocity of the liquid, in the temperature, and the falling characteristic of the tube inside surface. Owing to the large number of variables with many uncertainties, and the manufacturers have usually based their design on the generally proposed heat exchanger institute's standard for a steam surface condenser, and which is basically this equation. So the design of the heat exchanger mainly depends upon heat exchanger condenser basically depends upon this equation, which is we call the heat exchanger or heat condenser equation. So what is film-wise and drop-wise condensation? So the film-wise condensation happens if the condensate wet the surface and flows on the surface in the form of a film. So basically it forms a continuous film over the surface of the tube, and then the condensation takes place. So we call it film-wise condensation. And when the condensate doesn't form a continuous film and it doesn't wet this tube surface, and then the droplet forms, and then droplet slides over the tube surface, and then that we call it drop-wise condensation. So in drop-wise condensation, the heat transfer coefficient is high, and it is 4 to 8 times the film-wise condensation. So the drop-wise condensation usually occurs when the heat exchanger is new and the tubes are clean and polished, and after that it becomes dirty and the falling takes place and some oily film stick on the surface of the tubes, and then the drop-wise condensation does not take place, and it's mostly film-wise condensation which happens in the condenser. So in industrial condenser, usually the film-wise condensation occur. So when we talk about to design the shell and tube heat exchanger and find out the calculation or design calculation for the shell and tube heat exchanger, so the heat exchanger design is typically similar to the shell and tube heat exchanger. So the condenser design is very much similar to the shell and tube heat exchanger. So the heat transfer coefficient for the tube side can be calculated is a very similar way as the shell and tube heat exchanger. So shell and tube heat exchanger, for the tube side we calculate the velocity, Reynolds number, Nusselt number, and heat transfer coefficient. So the same way we can calculate the heat transfer coefficient for the shell and tube condenser. So the tube side treatment is same. The drop-wise condensation, when the condensate does not wet the solid surface. Okay, so this is covered already. So how do we do for the shell side? So as we said that the tube side treatment is almost same or exactly same as the shell and tube heat exchanger. As for the shell side heat transfer coefficient is concerned, so we will see the treatment on the next slide.